Hi, I'm Martin. We may have met. If we haven't, I'm sure we'll soon. Today's talk is going to be aimed at introducing you to linking your mech eng science and your design and manufacture. There's no point in knowing one and not being able to relate it to the other. So yeah, this video is going to sort of serve as an introduction to that. In front of me, there's a range of pumps. Go through them individually, and we'll start discussing why things are the way they are, and yeah, how to relate the maths, mech eng science, with the physical building. Okay, so here we have the first pump, centrifuge pump, impeller pump, motor on this side, pump head here. You'll see that there's some white tape, PTFE tape, so that means, well, that's to prevent leaks obviously, but it is crucially the liquid that was pumping does not eat PTFE tape. So yeah, here's the cap. Very simple casting, steel in this case. As you can possibly see, it's been repaired right there. It's been welded up. So yeah, when they do crack, they are repairable. You can also see on the inside there a little bit of the heat that's got in. And here's the actual, well, that's a gasket. Again, handmade, as you can tell by the shape of it. And this part here is the impeller. So liquid comes in here, spun by the motor, and is accelerated out through the fins here. That in turn comes up this hole, shoots out the top. Okay, you may be able to see inside there. And this sort of the slot, which starts very shallow and gets deeper and deeper, so that allows more pressure to be built up behind for it to shoot, usually upwards. Okay, so that's kind of that pump. It's worth noting how the motor, the electric motor part works. I'm sure most people know how an electric motor works. There's copper, there's magnets, and when you add electricity to it, it makes it spin. You don't really need to know much more than that. All the details on the electric motor can be found here. So let me zoom in a little bit and you'll see. Might see better if I put it in the correct orientation. There we go. So you've got your makers. It's terrible focus as well, isn't it? There you go. You've got your makers label, pump number, your input voltage 230. That's your standard standard household single phase supply. And at the bottom here you've got your pumping rate. So it's pretty hard to read because it's all worn and old. So that's kind of how you specify your pumps. Okay. So again, just to repeat, it's an impeller, centrifugal pump. The next one we have is the magnetic one. So very much the same. Very much the same. You can see that this plastic piece here looks the same as this head, does the same job. Motor goes in the center, accelerated out and up. this case in the center, accelerated out and up. Difference with this one is that there's not a physical join between the two. There's a magnet here, so it should be obvious there that that's what's connecting them. If I can, I'll pull it apart so you can see inside the pump part. Quite stiff. There we go. Okay, so 2 parts. And crucially, the O-ring. You need to factor in some sort of sealing device. And there's the pump there. That's just flings the water outwards to the wall, and as it goes up, it finds its way out. You can see there's residue in here from whatever it's been pumping. Presumably some sort of calcium-based thing, or sodium. So yeah, that's the magnetic drive impeller. So yeah, the magnet's in here. Don't know if you can see, it's sort of got a flat there, which means it's uneven, which means it sticks to the motor part. This also means that your motor can continue to spin if this part gets blocked up. So you're not going to burn out the motor. And when it comes for, this is broken, time to replace it. It's very simply just replace this part. Okay, moving on now to the sort of diaphragm style pumps. Again, the motor at the rear and the pump section at the front. In this case, inlet and outlet are both at the top. Well, inlet in blank, you can assume that this side used to say outlet. If I remove this head, you'll see the top of a piston. It's a very short travel piston, and the whole thing doesn't move, therefore it's a diaphragm. It kind of bulges like that. If I slide around the front cover, you'll see the rotational motion of the motor and this connecting rod getting a linear action from that. And then you'll see the diaphragm piston and the top there moving up and down. So this creates a suck blow effect inside this head. Now, if I can remove the screw from the top of this device. It's always worth, when you're designing moving components, considering how easy it will be to maintain. A component that breaks should be replaceable. It's just common sense. So, yeah, you can see here 2 empty tubes, clear tubes, and again that crucial O-ring forming the watertight seal. Inside here there's just a small bit of, it's PTFE in this case, and on the PTFE is before the mesh on the inlet side, and the PTFE is behind the mesh on the outlet side. When these end of these pipes are compressing that, it means that water will flow this way but not this way, because as the vacuum, as the not vacuum, sorry, as the diaphragm piston pushes back up, that's going to lift the PTFE up against this hole, sealing it. Similarly, as the pump draws its vacuum, it's going to push the PTFE against the other side of this face. See if I can remove that again. There we go. Push the PTFE against the inside of this face, not allowing anything to go back that way. So it can only go down that way and up that way. Hope that makes sense. Okay, and then reassembly, making sure everything's seated properly. Torque down as evenly as you can. Again, when you're designing, think about how it's going to go together. A single screw in the center is an excellent way of ensuring even torque, but if there's a lot of pressure required, if faces are mating rather than using O-rings, then you may struggle to do that. So instead you'll have to either have fully threaded components, or you cross tighten your screws as you go. Okay, so that's how this particular diaphragm pump works. The next one is the big yellow one. This is going to be impossible to see on the screen. So if I place it on its side, it may be easier. Fluid goes in here and out here. Okay. You'll see, I'll remove this part first. What I'm expecting to happen is a ball to fall out here. Right? So there's the ball. You can see inside here there's 2 holes, which means that water or fluid, whatever you're dosing, can go past the ball. It goes into 2 holes. Yes? Whereas on the top of the head part, you'll see a single hole, which means that the ball, put it back in, will seat, and therefore the fluid will not be able to pass back the way. Opposite is true on the other side. Your inlet, you can maybe see the ball inside there, means that the fluid can only flow this way. So as a whole, fluid flows from bottom to top. Okay, now I'll try and remove this head as well. Maybe sometime, so bear with me. Yeah, these pumps are generally used for things like dosing chlorine into swimming pools. Very similar to that. There's a control panel on the other side, and that will allow the user to decide how often, how quickly it's pumping. Whereas, the other, the centrifuge pumps are far more likely to be either on or off. Yeah, so if you're having a constant flow of liquid, then you're probably going to use a centrifuge. If you're dosing chemicals into a system, you're probably going to be using a diaphragm. So there we go. There's the head, again, 2 at the bottom, 1 at the top, fluid's flowing that way. there's the diaphragm component. Goes in and out, which forms that vacuum and that pushing pressure inside the head and creates the fluid flow. Okay, briefly mentioned, on the back there's your control panel, so your speed and your stroke. These can also be sort of remotely computer controlled, where, you know, if the fluid concentration drops below a certain point, it engages the pump, and vice versa. Okay, so that's the diaphragm style pumps. So if I was needing to put these things into practice, design something, design a system, I would first start with a list of requirements. Okay, so let's use the swimming pool analogy again. And list of requirements: it pumps. You need water flowing through the system, right? So water must flow constantly. You need to also have a heating system. Water must be heated. The water must be cleaned, so you must have a filter system, so water must be filtered. And to keep it clean, usually there's a chlorine dosing system. So chemical dosing. Okay, so that's the requirements. You then go on to like make a chart, make a table, and across the top of the table you might write concepts. And down the side, the functions. Okay, so go across like that, like so. So, concepts: water must flow constantly, so I guess you would write centrifuge pump. Water must be heated, so heating system. Just write heaters. Water must be filtered, so filters. And chemical dosing system. So for that, as we alluded to earlier, you'd have the diaphragm pump. Okay, so the function of the centrifuge pump simply constantly pumps the water. Constant pump H2O. It's not H2O because there's other chemicals in it, but that's the picture. Heaters. Most places use gas to heat things, right? So warm water to, depending on your own preference, the swimmers amongst us will like the water a little bit cooler, 28 degrees possibly. The leisure swimmers amongst us would probably prefer the water around 31, 32, and the non-swimmers may just like a bath at about 40. 40 may be a bit hot. So we'll say 30 degrees. Next, filters. Yeah, so media filter takes out this non-dissolved solids. So just a media filter. No. Media filter would go here. Filters, so removes dissolved solids, or removes non-dissolved solid. Removes non-dissolved solids. And the diaphragm pump doses system. Alright. So, in here, centrifuge pump, constant pumping of H2O. That pump needs to be able to pump the water through the heaters, through the filters, and still allow the diaphragm pump to dose. So these are all things to consider. The water's at 30 degrees, so we need to be sure that, okay, that's not very hot, but if it were a higher temperature, the centrifuge pump can handle that. The heaters themselves need to be able to cut on and off to maintain, so there needs to be a temperature checking device. Filters, again, a media filter may be prone to change depending on the temperature of what's flowing through it. And the diaphragm pump, again, you don't want overheating issues. Removing non-dissolved solids, you need to think of how your system's built in terms of filters before the pump, possibly. You don't want solids flowing through the pump, or you maybe want a pre-filter just on the inlet, before the inlet of the pump. Again, the heaters, that generally involves coils or the like, so you don't want a blockage in there. So again, you'd probably go filters, pump, heaters, diaphragm pump. It's an inlet from the side, so it's probably less important. Dosing system. Your centrifuge pump needs to be able to pump more than just water. If it's likely to get, choked up with chlorinated water, that's a consideration. If the pressure builds too high, the pump can overheat, can cut out, or it can simply clog up. Again, the heaters with the closed coil system, clogging up's a potential issue. And the filters, you need to get your dosing system correct before your filters, so they don't overheat, or not overheat, they don't get choked up. Okay, so it's important to have good controls in place. So once you've filled all that out, you then go on to looking at options. So using your maths, your engineering science, knowing the pressures you're going to need for the size of the pool, the volume of water, how much water you're going to pump. These are all questions you need to answer as well, and they can be answered with maths. So say you've got 250,000 gallons. You're going to need to convert this into SI, obviously. Then you're going to need to figure out what length your pipes need to be, how many pumps you're going to require, what sort of heating you're going to need, Again, your filters have to handle that volume of liquid, and your diaphragm pump needs to be strong enough to dose at a level that is going to, dilute's not the right word, get your chlorine level to sufficient. So yeah, that's where your maths comes in at the end there. And then we can insert specific concepts. So my centrifuge pump is going to be model X that pumps at the rate Y. My heaters are going to be able to heat P amount of water to Q temperature. Filters are going to be able to filter said amount of water, and yeah, your pump's going to be able to dose enough into that system. Okay, so this is not an example you're going to be using, but it's a sort of thing where linking the two things together, and that's pretty much all I have to say about it. Hopefully it was interesting.